Okay, so so far, continuing from last week, we've been talking about how to quantitatively calculate the concentration of electrons. I'm trying to get to the slide again. The quantitative expression for the concentration of carriers, electrons and holes. And recall that in the case of semiconductors, we have three situations. One is we have intrinsic materials where there are no impurities. And then secondly, we have extrinsic materials where you have donors or acceptors. Now, when you have extrinsic material, the calculation is very straightforward, right? Because if you have enough donors, the number of electrons, in the case of donors, is approximately equal to the number of donor atoms. So it's pretty straightforward to calculate, right? And the same thing for acceptors. If you have enough acceptors, the concentration of holes is approximately equal to the number of acceptors. The problem comes when you have to calculate the minority carrier concentration. Okay? That's why we worked on. And then we talked about the concept of the Fermi level, which is essentially an energy level where the probability that that level is occupied is 50%. So anything above that level, probability of being occupied is lower. Anything below that level, probability of being occupied is higher than 50%. That's the conceptual way to think about it. Of course, we also need to know how many states are available. So you multiply these two things together, the Fermi distribution multiplied by the number of available states will give you how many electrons could exist, right? Then we talked about how it's dependent on temperature and so on and so forth, effective mass and so on. Okay? So make sure you're fairly clear on those concepts. We went through them quite fast, so I would highly recommend going through them slowly. Which is why I'm recording the screen, so you can stop that, slow down, think about it again, as opposed to real time. Okay, so the rest of that topic, we are going to talk about the temperature dependence of carrier concentrations. Now, this is important because certainly, first of all, they show interesting phenomena. The materials behave very counterintuitively based on how temperature changes, so as we will see. Second of all, it's important for real devices. Real devices could be operating in Mars, right, or Moon, where the temperature is minus 100 degrees Celsius, right? Or they could be in the middle of a tank or something where it could be over 150 degrees Celsius in Afghanistan or whatever, right? So you have to understand there's a huge range of temperatures that these devices have to operate over, and we need to really understand what happens with those ranges, and they have to be designed for those ranges, right? So anyway, from a very fundamental perspective is what we're going to talk about today. Okay, recall, we saw that last class, okay? So that's essentially the concentration of the carriers at steady state, at equilibrium, okay? Till now, we've only talked about equilibrium conditions. We haven't talked about non-equilibrium, which we will talk about later on. So don't worry about anything else. So that N0 here refers to equilibrium, not steady state. Okay, so the concentration of electrons is equal to some intrinsic concentration of electrons. This is for the intrinsic material, multiplied by an exponential factor. Okay, the exponential factor is essentially the difference of the Fermi level from the intrinsic Fermi level. Okay, divided by kT. So if you have donors, this number is positive, right? EF is greater than EI because you have more electrons. Of course, then N0 is greater than Ni, exponentially. Okay, you see that quantitatively, but you need to understand this conceptually, so I'm trying to emphasize that. Same thing happens for holes. Okay, that's the whole concentration at steady state. That's the whole concentration of the intrinsic material is the same as the electron concentration in the intrinsic material, so it's the same number, Ni, right? Recall that, because they're always generated in pairs, times another exponential factor, which depends on the difference of the Fermi level from the intrinsic Fermi level. But now it's a negative sign. Okay? So as you see, as the Fermi level goes below the intrinsic level, this number is positive, and the hole concentration is higher than the intrinsic hole concentration. Okay, so you see that dependence. Okay? Okay, be very clear about that. That's quite important. Another important thing you'll see in this very simple equations, if you multiply them together, what happens? What is this? What? Someone speak up. I can't hear you.
Ni squared.
Yeah. Which means it doesn't depend upon the Fermi level. Doesn't depend on how many donors or accessories there are. We'll make use of this. In fact, you will use this in your problem sets. Okay? Okay, but we are today, right now, interested in the temperature dependence. Okay, clearly there's an exponential there's a t in the exponent, so we expect that to have some dependence. But the intrinsic concentrations are also temperature dependent. Remember, if you heat the material, the more of the electrons in the valence band go up to the conduction band, right? So that's expected. We know what that dependence is. We saw that last class. It is given by this term, square root of NC and V, and some exponent, which depends on the band gap. Okay. Now, these two terms, if you recall, were the effective density of states at the top of the conduction band, and at the bottom of the conduction band, and at the top of the valence band. Right? There are those two terms which depend on the effective mass and so on, as follows. Like we have that expression shown here. Okay. And it depends on the electron effective mass. Also depends on temperature. Right? Same thing for the holes. You have a hole effective mass and temperature. We put it all together in expressions which looks like that. Okay. So if you look at the temperature dependence, you have a T raised to 3 over 2 there. And there you have an exponential term. Minus Eg over 2kT. Okay. Of course, when you put this together, the exponent will dominate. Okay. So, as temperature increases, what happens? If you just think about the exponent, what happens to the exponent? This kind of logic, it's common sense, and you should be able to do this. Okay. Much more important than doing the math, in my opinion. So, as temperature increases, what happens? Yeah, so 1 over T decreases as T increases, yeah, right? So remember, e raised to minus, let's ignore all the constants and just write that, okay? This is nothing but that, right? As T increases, this whole thing decreases. This whole thing, what happens? Decreases, right? The exponent decreases, the exponential of that. This whole thing increases. Okay. So, of course, you need to make that logical progression. It's very simple, but you need to understand that. So, clearly, as temperature increases, this whole thing increases. Again, okay? As this increases, that decreases, that decreases, that increases. Okay. Follow the logic. It's okay if you miss it right now, but make sure you're able to do it, I hope. Okay, so if you plot it, oh, okay. Okay, one more thing before we plot it, yes. So this is important to actually do problem sets and so on. So let me just point that out. So we have this very simple set of equations. Now, if the Ni is known, which is the intrinsic concentration of carriers, electrons or holes in some material, it's material dependent, silicon, gallium arsenide have different numbers, and the Fermi level relative to the center of the band gap, which is the intrinsic Fermi level, is also known at a given temperature, then we can calculate how many carriers are there. So, for example, if I gave you a band diagram, this is the valence band, this is the conduction band, and this, let's say, is the Fermi level, and I told you what the temperature is, you know everything about this material. In principle, of course, I also have to give you an eye, or I have to tell you what the material is. Do you see that? Okay. Because with an eye and this difference in energy and temperature, you can calculate N naught. If you know N naught, You can calculate P now from here. Okay? You have to make that logical step. So keep that in mind. Now, of course, if the material is extrinsic and it's heavily doped, then it's much simpler. Like I said in the beginning, that if it's a donor, the electron concentration is just the same as the donor concentration. Okay? Now, if we know that, then we can explicitly calculate the Fermi level as well with respect to the other levels. Okay. That in mind, now let's look at the plots of the carrier concentration. So this is the intrinsic carrier concentration. Okay, so let me go back and recall. What we are plotting is this equation as a function of temperature. Okay, keep that in mind. That's the intrinsic carrier concentration, electrons or holes, of different materials as a function of temperature in log scale. Okay, so this is Ni. Units per centimeter cube. Oops. And this is temperature. Okay, in kelvins. Now, also shown on the top. Oops. In kelvins. So you can see, of course, it is an exponential increase. It's plotted in terms of 1 over T. That's why. Okay, this is 1 over. Oops. Sorry about that. But the horizontal axis is 1 over T. As 1 over T increases, T decreases. So going this way is cooling the material. Going this way is heating the material. Okay, going right to left. So as you heat the material, the intrinsic concentration increases. Linearly on a logarithmic plot means it's exponential increase. Okay, which is obvious. And you can see the representative numbers at room temperature, which is 300 Kelvin. Okay. For silicon, as we recall, it's about 10 raised to 10 per centimeter cube. For germanium, it's 10 raised to 13. Gallium arsenide, about 10 raised to 6. Okay, this is a percentage number. Again, I don't really care if it's the order of magnitude. That's much more important at this time, in any case. So I just dropped the other terms. Okay, so keep that in mind, because this is quite important to understand what happens to the material as we heat it. Okay, that's what's plotted. So let's think about a thought experiment. You take a slab of silicon, okay, and it's isolated from everything else. You start at 0 Kelvin, very, very cold, and start heating it slowly. Okay, and let's say it has some donors in it, some arsenic or something like that. Okay, what happens to this carrier concentration? Okay, heat it very high. Okay. Yes, it should go up, but it will behave differently. That's what we're going to talk about. Of course, it does go up. So that's shown here. The horizontal axis, again, is 1 over temperature. So go from the right to the left. As you heat the material, you're going to start at the right, go to the left. Okay? The vertical axis is the concentration of electrons. A steady state, and not. Okay? So let's see what happens. Start from the beginning. Very cold. And this stuff is at 0 Kelvin. Nothing is moving, right? No electrons, crystal, everything is at standstill. Okay? What that means is that the electrons that are attached to the donor atoms remain attached to the donor atoms. They don't get into the conduction band. There's not enough energy. Okay. Recall the donor energy. What happens when you have donors? You have an energy level here, not the Fermi level, some energy level here. This represents the donors. And those electrons can jump up here, right? And they need thermal energy. So if you have 0 Kelvin, there's very low thermal energy. That doesn't happen. So the donor, okay, I don't see any eraser, but the donor electrons get stuck to the atoms. So the material is essentially an insulator. Right? Silicon is an insulator. The concentration of electrons is very low. Okay. As you increase the temperature, the donor atom starts ionizing. The electrons do this. They gain energy and start jumping up into the valence, into the conduction band. So it's called ionizing because arsenic is losing an electron. It becomes an positive ion, right? We'll talk about that soon. Keep that in mind. Arsenic loses an electron, it becomes a positive ion. So it's called ionizations. Okay? Now, after some temperature is reached, all the arsenic atoms have given up the electrons. Okay? So it saturates. No more. Okay? That's what happens here. Okay? So whether you increase the temperature or not, there is no more electrons to be given. Okay? So it just remains constant. So here carrier concentration is equal to the donor concentration. That's the situation we talked about before. All donors are ionized. Okay? What happens if you keep increasing the temperature? Something strange happens. Now, at very high temperatures, the electrons that are here have enough energy to jump up here. So that's the intrinsic electron hole generation, electron hole pair generation. Right? So these electrons starts contributing at very high temperatures because they now have high energy. I mean, this is a big energy gap. So if you have enough temperature, you can jump up. And that's what happens here. There, these electron hole pairs start dominating. Now the material starts behaving more like an intrinsic material. So that's what's peculiar about this behavior. Okay? So at temperatures which are very low, it's just an insulator. Nothing happens. At reasonably high temperatures, it acts like an extrinsic material, like we talked about. At very high temperatures, they start acting like an intrinsic material. So keep this. That's why this temperature dependence is important. It shows this peculiar behavior. We need to design for it. In practice, it's much more favorable to use the concentration of the donors or acceptors to control the electron or hole concentrations respectively rather than temperature. The temperature is harder to control. So you want your device to essentially operate here where the carrier concentration doesn't change much with temperature. That's where you would like it to be. Because you don't want too much temperature variation. You want the same device to operate properly, whether it's 0 degrees or 100 degrees or whatever. Okay? So what you do is you try to keep the doping high enough such that you keep this flat over the temperature range of interest for operation of the device. So for practical, as an engineer, when you design these things, that's what you do. Okay? So that's why, again, the temperature dependence is important. Go back and think about it. Make sure you understand it qualitatively. Okay. So the next topic we need to really understand is compensation and space charge. So this is a little bit different, but again, it's not that complicated. So let's think about it a second. Before I jump in, so recall, if you have, say, a slab of material, the bulk of this material is typically charged neutral, meaning there's no, unless you apply charge to it or import charge to it, there are no charges in there. They're not positive or negative, which means there are an equal number of electrons and an equal number of positive charges, because electron is a negative charge. Okay? And that's what's referred to as the space charge neutrality. This principle turns out to be very important to understand devices. And we will apply this again and again for PN junctions, for transistors, everything. So this concept is important. That's the idea that the materials, unless otherwise stated, the materials are charge neutral. There are an equal number of positive charges, equal number of negative charges. Okay? So keep that in mind. That's the basic idea. So let's ask a question. What happens if a semiconductor has both donor and acceptor atoms? Okay? From an energy level perspective, what that means is, of course, you have a valence band, you have a conduction band, and you have some intrinsic Fermi level, you have an actual Fermi level, and you have a donor energy level, and you have an acceptor energy level. Okay? That's what it means. You have both arsenic and you have boron. This is also possible, right? In fact, it's pretty common. because on the same wafer, you want to make N-type and P-type transistors. That's how it's almost all the chips, for instance, in these computers and so on are made. So they exist. So let's analyze what happens here first. First, I'm going to ask you to do a practice problem. This example is a semiconductor N-type or P-type. 10 seconds. Discuss it with your neighbors, actually. Don't shout out the answer. Okay? Look at the energy band diagram. Talk to your neighbors. Tell me, is the semiconductor N-type or P-type? Or go talk to him. Okay. Let's see. Someone wants, not you, someone else. What's N-type? Or is it N-type or P-type? Someone shout out. Yeah. Why? What's a simplest way to say it?
The Fermi level is higher than the...
Yeah, exactly.
Level higher than the
Intrinsic level. Yeah, that's what we said, right? Very simple. Of course, you can also just look at the electrons. There's many more electrons than holes. Okay? They're fine, but make sure you get a feeling for how to read these things. It's very important. Okay, now let's think about what's happening here, first of all. So let's look at the donor atom, donor level. Pretty straightforward. The donor electrons are basically donated to the conduction band, right? Nothing fancy about it. Gets enough energy, goes up. Next thing, for the acceptor level, same thing. The electrons from the valence band just jump up to the acceptor level. Okay, leaving holes behind. But in addition to this, something more can happen. Okay, you can have, so you have a large number of electrons here, a fewer number of holes here. You can have a recombination of these electrons with these holes. Okay, it means you can have this situation happening. Some of the conduction band electrons will recombine with the holes and essentially lose energy, as heat, or typically as heat. As a result, so in this case, this is N-type because, first of all, before we go on, the number of donor atoms, or the donor concentration, is much higher than the acceptor concentration. That's why it's N-type. Because that's why the Fermi level is about the intrinsic level. Okay? Keep that in mind. But this happens, okay, in equilibrium. So all of these processes are happening, but in equilibrium, the three things happening. Again, keep that in mind. One, the electrons being jumped up here. Okay. Two, the electrons coming up here. And three, this recombination is happening. These three processes are working together to reach a steady state. Okay. So keep that in mind. It's not a static situation. It's not a snapshot like this. It's always happening, but in a statistical equilibrium, all of these have to match. The generation and recombination have to match. Okay? In equilibrium, as a result, the net concentration of electrons in the conduction band becomes Nd minus Na. Okay? Nd is the number of electrons that have been generated up here. Na is the number of holes that have been generated down here. If you subtract them, because there's recombination happening, it gives you the effective number of electrons that end up on the valence conduction band. Okay? So if you have both donors and acceptors, the concentration of electrons is Nd minus Na. Now, you can have the opposite type, P-type, where Na is greater than Nd, then the number of holes is Na minus Nd. Right? Same argument. So, but keep the physical reality in mind on how that happens. Okay? And this concept is called, compensation, where these electrons here are compensating for the holes down here. Okay? Also, so another way to think about this is that what this means is that you can keep adding donors. Okay, you can change a p-type material from p-type to n-type. Right? I can increase ND. Let's say you start off with a p-type material. I can increase ND until they're equal, and then it becomes intrinsic. And if I keep increasing the donors, it becomes n-type. So I can change. Okay, and this is exactly what happens when you make CMOS transistors that drive all the chips today. You start off with a certain kind of silicon, you make a transistor. Okay, and then locally, you need to make the other kind of transistor, you add the other stuff. Okay, so you make it to the other type. Approximately. Okay? Okay. Now, so let me go back to this picture again. If you look here, the number of negative charges here is determined by the number of electrons. The number of positive charges here is determined by the number of donors here. Right? The donors have positive charges because they lost an electron. The acceptor atoms, the donors up here, the acceptor atoms have gained an electron, so they're negative charges. If you add up all the negative charges, that should be equal to all the positive charges. Okay? That's what's called space charge neutrality that we talked about earlier. Okay? So to quantitatively do this, we need to do the following. You need to add the number of holes to the number of ionized donor atoms, which are positive because remember they have lost electrons. That's all the positive charges. That should be equal to the number of electrons plus the number of ionized acceptor atoms. Acceptors have accepted the electrons, so they're negative. So all the negative charges should balance all the positive charges. Okay? So the entire material must be charged neutral. Okay? Now, of course, if the material is n-type, n0 is much greater than p0 by orders of magnitude. So we can ignore p0 in this equation and just say n0 is more or less equal to nd plus. Okay? That's the same, nd minus na, which is what we just talked about, the compensation. Okay? That's pretty obvious. Okay. So that brings us to the end of this. So far we have looked at carrier concentrations, okay? And in the next step, we are going to use the carrier concentrations to calculate currents. So let's bring this up. Okay. Okay, now we know how to calculate the concentration of carriers, electrons, and holes. Next, we need to calculate how they move. Okay, but before we do that, let's think. There are two ways that this happens. One is in the presence of an electric field, these things drift. Okay, and you can also have this in the presence of a magnetic field, as we'll talk about. But before we go into it, let's see a very brief video of what it looks like, so you have a feeling for this. Okay. And this is a nice simulation that these, okay, I have to get out of this first. These scientists did. It shows what happens. Okay, so here, it's hard to see, but the electrons are red and the holes are blue, I think. They're just floating, no field is applied, okay? They're just moving around thermally, random motion. You apply a field, you see what happens. The electrons, which are in blue, move opposite to the field. They slowly drift that way. And the holes slowly drift in the direction of the field. And this is basically what happens. Okay, I want you to keep this picture in mind as we look at this quantitatively. Okay, it's a little bit hard to visualize. That's why that animation is kind of nice. Okay, so with that picture in mind, we will try to quantify that, essentially, that current. Okay? In order to quantify that, we need to introduce two new concepts, conductivity and mobility. Mobility turns out to be the most important parameter, as you will see in some of the examples we'll see today, for a device performance. Okay, mobility determines how fast a transistor can switch, which of course is the basis of all modern electronics, right? Faster processors, faster computers, and so on. So it's mobility that's really key. Okay, we'll talk about that. So first, let's talk about thermal equilibrium when no field is applied. At thermal equilibrium, all electrons essentially randomly move around, like we saw in the video. They randomly scatter from lattice vibrations. They also scatter from other. They can collide with other electrons. They can collide with defects in the crystal. They, of course, are also colliding with the ions, which are positively charged. Right? So all these fields and all this, they just collide with each other. So they basically randomly move. So it has a little bit of energy, so it just bounces back and forth, so on and so forth. Right? Some sort of random motion. As a net result, the electron doesn't go anywhere. Averaged over time, or averaged over a large number of electrons, nothing happens. As we saw in the video, right? Just jiggle around, no current. So keep that in mind. Okay? As soon as you apply a field, as we saw in the video, the electrons, of course, will see a force, which forces them. The field is applied in this direction, Ex. The electrons will move opposite to the field, just like we know from, our currents from Ohm's law and all that stuff. Okay, and the velocity of the electron is given by. Oh, we'll come to that later. So let's not go into that. So our goal now is to understand how the electron moves in this field. Of course, that motion of the electron is the current, right? So that's what we want to know. Okay, so in order to understand the motion, we need to write the forces. Okay, so the first force is there are two forces. Okay, we'll talk about. The first force is the force of the electric field on the electrons. It's very simple, because the force is just the charge of the electron multiplied by the electric field. If you recall your high school or undergraduate statistics, electrostatics. Okay. Of course, force can also be written as change of momentum. Okay. You must recall, force is mass times acceleration. This can also be written as change of. You see how this comes from? Because this is. Okay, acceleration is just change of velocity times mass. Mass times velocity is momentum. So you bring this in. Just change of momentum, right? Straightforward. So force shown here is Q times E times N, because there are N electrons per centimeter cubed, and we are averaging over all the electrons. Okay, and there's a negative sign because it's opposite to the field direction. Okay, if we have holes, that will be a positive sign. Straightforward. That should be equal to change of momentum of the electron. Okay. Now, if this was the only force there is, this electron will just get accelerated in the field, right? If you look at it, this whole thing in this case is equal to minus Q and E. This is a constant, right? Q and E. Q is just the electronic charge, and it's just the concentration of carriers. This is the field. This is constant means if I do the integral, let's do the integral very easily. So remember, this is okay. That's the equation, right? You do the integral. What is velocity? Becomes minus Q and Ex times T, right? If you start from 0. Okay, just integrate. It's constant, it's easy to integrate. What does that mean? That means if I plot velocity as a function of time, it's decreasing forever. Does it make sense? That means the electron velocity is increasing, absolute velocity. It's accelerating off forever. Of course, that's not what happens. Okay, because it's steady state. There's no energy input here. What happens, of course, is that there is an effective deceleration that happens as the electrons collide with the crystals, with the crystal vibrations and so on. So this acceleration in the field is balanced by collisions in the crystal and other collisions, electron-electron collisions, electron defect collisions, and so on. So we have to do the other force, which is the decelerating force calculation. Okay, that's the next step. That's a bit more complicated. It involves statistics of random processes. Okay, because the electrons collide randomly with everything else, right? What that means is that the probability of collision of an electron is a constant number because it's a random process. There is no reason it should depend on anything. It's a constant number. Mathematically what that means from your basic probability is that you can write this equation. The number of electrons that have not undergone a collision as a function of time can be written as some constant, we'll talk about that in a second, multiplied by the number itself. So think about a situation, you have some n electrons. At the beginning of time, none of them have collided with anything else. Okay? As time progresses, more and more collide with something. The concentration of those electrons that have not undergone a collision is proportional to the number of the electrons that have not undergone a collision. Sorry, let me restate that because I said that wrong. The probability that a collision occurs, the first collision occurs, is of course proportional to the number of electrons available to undergo the first collision. Okay? So, you can write an equation which looks like this, where the change of rate of concentration of electrons that have undergone a collision is proportional to the remaining electrons. Okay. Don't think too much about it, but you can go back and read it. It's not that complicated. I'm not saying this the most clearest way possible, I guess. So n is the number of electrons that haven't undergone a collision by time t. dn over dt is 1 over t bar, some constant, times n of t. Now this equation is very easy to integrate, right? Because this is a constant, you can bring this down, do an integral, you get a logarithm, that becomes an exponent, and so on. I'm not going to do that, but you get a solution which looks like this. Okay? This sort of processes, by the way, are very, very common in physics. For those of you who might have seen radioactive decay and all this, these kinds of random processes that modeled in the same way. Okay, so the number of electrons is now given by some constant n naught, which of course is the number of electrons that are not collided at t equals 0, that's the original population of electrons, times some exponential term, e raised to minus t over t bar. Now if you plot this, so this time, this is n. You start at t equals 0 at some number n naught. It exponentially decreases. Right? That's what this equation looks like. At some t equals t bar, what is this? Let's just plug in. What happens? T equals t bar, e raised to minus 1. What's e raised to minus 1? It's 1 over e, right? So this number is just n naught over e. Okay? E is exponent, right? 2.7 or something like that. In other words, the t bar is equivalent to the half-life, if you recall. It's the half-life of radioactive species and all that kind of stuff. In our case, it's a little bit different. It will be called the mean free path, or mean free time, sorry. It's the average time between collisions. So that's a way to think about it. So if you start with a cloud of electrons in a crystal, start time t equals 0, and plot the number of electrons that have undergone a collision or have not undergone any collisions, it will look like that. Okay. After some small amount of time, all the electrons have undergone collisions. Basically, that's what that says. If this t bar is very small, this goes to 0 very fast. It's exponential, right? Actually, this should go to 0. My plot here is wrong. Basically go to 0. Okay. So now we can calculate what the force from these collisions is, what the effective force from these collisions is. That's preventing the electrons from being accelerated. Okay? So again, to reiterate, the probability that any electron undergoes a collision in a time interval dt is just that constant, which is 1 over t bar times dt. Okay, that's our original assumption for random processes. And the change in momentum in time dt is the momentum of the electron multiplied by the probability that it has undergone a collision. Here we are assuming that you are undergoing what are called elastic scattering events. Okay? Don't worry too much about the details of this, but you should at least follow the logic of the math. Okay? Now, if we can write the change in momentum in this manner, then of course that's all we need. Now we can calculate the force, right? Because the change in momentum per unit time is force, as we saw here. Okay? So of course, change in momentum per unit time is just you bring that dt down, and that's the force from the collisions. Can be written as minus px over t bar. The negative sign is of course because it's decelerating, right? It's decreasing the momentum. Remember, the electric field was increasing the momentum in the negative direction, but that's okay. It's increasing the momentum. Here it's decreasing the momentum. They have to balance out. The steady state. This is deceleration, that's acceleration. In steady state, there's nothing. It's constant velocity. Okay? So, at equilibrium, there should be zero net force, and we can set them equal to 0. So, this is the force due to collisions, or the force due to collisions, deceleration. That's the force due to the electric field, which is acceleration. Add them up, they should be 0. Okay, pretty straightforward. Then you can calculate what the average momentum per electron should be, which is just bring this to this side and do px over n. Because remember, now we're talking about n electrons, which is a large number, 10 raised to 10 or so. What is the average momentum per electron? Divide the total momentum by n. And you get a very simple expression, minus q t bar ex. Okay. So what this is saying is that the electron is now moving at a constant, average constant velocity. But again, recall the video we saw. Okay, the electrons were jiggling around. You apply a field, and they still jiggle, but they slowly make their way to one side. That's what happens in reality. So when we talk about velocities and so on, it is the average velocity. Because remember, electrons are still moving randomly. Whatever way you want, but slowly moves randomly in one direction, as we saw in that video. Keep that picture in mind. So when we talk about velocity, it's the average velocity. This is the average velocity with which it has moved, opposite to the field. Okay, and that's basically given by px over the mass of the electron. Okay, but of course we still have to be careful. This is the effective mass of the electron, because we still need to account for the lattice potential. And that effective mass is now a little bit different effective mass than before. We'll talk about that in a second. So the velocity is just given by qt bar over mn star times the electric field. Okay? Pretty straightforward. So this is the net drift velocity of the electron for an applied electric field. Okay? Now, to calculate current, you have to look at what is the transfer of charge, right? One electron has 1 q of charge. N electrons have n q's of charge. And they move at certain rate. So to calculate the current, you have to take the velocity of the electron, multiplied by the number of electrons, multiplied by the electronic charge. Okay? Of course, we are talking about unit volumes. When you talk about unit volumes, this becomes what's called current density. Okay? And in order to explain that, think about the material and imagine a cylinder within this silicon, whatever material. The electrons are moving. Okay? You apply the field. The electrons are moving this way. if you have a unit area here, and the length here equal to the velocity, the total number of electrons which are within the cylinder, which pass through one face of the cylinder and out the other, is given by n, concentration of electrons, times the volume of the cylinder. Right? Volume of the cylinder is just this length of the cylinder times A. In one unit time, 1 second, electrons will move from here to here, right? Because that's velocity. Right? So this times Q is the number of charges in 1 second that I moved from here to here. Okay? If I divide that by area, I get the charge per unit area. Charge transferred per unit area, per unit time. Okay? So this way, this is nothing but charge by time times area. Charge times time, charge divided by time is nothing but current. Right? Current by area. Okay? That's what that is. Q and Vx is just current per unit area, or current density. So again, looking at the units, Q is coulombs per electron, that's the charge per electron. N is electrons per centimeter cubed, concentration. Velocity is centimeter per second. You multiply these out, you get amperes per centimeter squared. Ampere is nothing but coulombs per second, right? It's current. So you see the logic there. Okay. Now, so you get an expression like that. So you plug the value for Vx in from before, you get nq squared T bar over Mn star times Vx. Now recall from Ohm's law, current is related to electric field by what's called conductivity. Okay. Remember, you might have seen Ohm's law's current voltage. I forget. V equals I times R, right? That Ohm's law. It's been too long for me. You can write it that way. 1 over R is the conductivity, and you see the relation. No? V per unit length, and if I do that, V per unit length is the field. Current per unit length is basically if you take a unit volume, that's just the current density. And then S becomes conductivity of the material. Okay? Anyway, go back and look at it. I might have made some mistake. I don't really remember the actual expression. But Ohm's law, basically, if you write it in unit area, becomes current density is related to electric field by a constant, which depends on material, which is conductivity of the material. Okay? Sigma is the conductivity. Now it's given by nq squared T bar over Mn star. And sigma can also be written as Qn mu n. Okay? So Qn mu n. Mu n is an important quantity which refers to the mobility of the electron. It's the electron mobility. And from here we can see mu n is just related to Qt bar over Mn star. What's important about mu n, the electron mobility, is that it only depends on the material. Depends on the electron effective mass, which means it depends on the band structure. It depends on T bar, which is the probability of collisions, which turns out to depend on how many donors are there, how many defects are there, and so on and so forth. We'll look at that. And this quantity turns out to be very important. So keep this picture in mind. The mobility, if you also, I think it's in the next slide. Let's go back. If you take this expression and plug it here, you will see, actually, let's write this down. This is an important relationship. Okay, so sigma is n, q, mu. I'm going to drop the x's and all that, okay? So mu is sigma over q, okay? So if I plug in J is sigma times E, which is n q mu times E, and but J is also given by the top, Q, and I'm going to drop the signs and all that. Understood what it is. Okay? So now mu, you see why mu is important. Is the velocity gained by the electron per unit electric field. You see that? That's why it's important. It's a measure of how the electron responds to the field. The higher the field, the higher the velocity, more or less linear, and the linear coefficient or the proportional coefficient is mu. Higher the mu, the more the electron will respond. Faster it will respond, and so on. Lower the mu, the slower it will respond. That's why it's important. Okay? Okay, so how do we calculate the electron effective mass? It's different than the density of states effective mass, because there are two different quantities we're trying to calculate. Earlier we were trying to calculate the number of available energy levels. Here we're trying to calculate the mobility of the electron. Two different things. Again, I won't go into the details, but just remember that they're different. So this conductivity effective mass is different than the density of states effective mass that we use to count the number of electrons. Recall in silicon, the equi-energy diagram looks like this, where you have two masses. You have a transverse mass MT, and you have two longitudinal masses ML. This is at the bottom of the conduction band. There are 6 equal directions in silicon at the bottom of the conduction band in the three-dimensional space. Okay? Turns out that the effective mass for conductivity is given by what's called the harmonic mean. It's 1 over 3 times 1 over m plus 1 over m plus 1 over m. 1 over m1 plus 1 over m2 in the three directions. Remember the density of states effective mass was what was called the geometric mean. So they're different. Okay. In the example problem, from the text, it says to calculate the conductivity effective mass of electrons in silicon, and you don't need to do it, but let's just look at the numbers to get a sense of what those mean. For silicon, ml is 0.98 m naught. M naught is just the mass of the electron, usual mass of the electron. So you can see ml, which is the longitudinal direction, is much larger than the transverse direction. What does that mean? From the band diagram. Remember, effective mass is inversely proportional to the radius of curvature of the band diagram. So if the mass is higher, band radius of curvature is lower. It means that in this direction, the band is less curved than in this direction, basically. Okay? So there are 6 equivalent x values in the conduction band. So the harmonic mean is just 1 over 3 times 1 over mx plus 1 over my plus 1 over mz, and you get something like that. Okay? So it can be considerably smaller than that of the electron itself. That's shown here. It's about a quarter of that of the electron. Okay? By the way, this turns out to be an important parameter. Okay? What this means is that by controlling the band structure of the crystal, I can control the mobility of the crystal. Well, mobility of the electrons in the crystal. Okay? Now recall for gallium arsenide, that diagram was a sphere. It's the same. So what would be the answer? The harmonic mean for gallium arsenide these numbers are all the same. All these are the same. Just that, right? Okay, it's the same as the geometric mean. Okay, so as I said before, the mobility, another way to look at it, is defined as the average drift velocity per unit electric field, as we saw, as we just derived. Velocity is opposite to the field, so mobility is always positive. Mobility is always positive. It's meaningless. It's science. But keep the signs in mind. I ignored all of them in this graduation. As long as you're aware of how they are moving, it's okay. Okay. Oh, yeah. So what are the units of mobility? As an example problem for you. So again, discuss with your partners. What is the unit of mobility from this? Take 10 seconds. Okay. Talk. I will start asking so you guys actually discuss now. Okay, someone tell me. Let's do one thing at a time. What are the units of velocity? All right. What's the unit of field? What? No. What are the units for field? Volts is potential. Volts per meter. Okay, recall from statics. Volts is just the potential, yeah? Has to be over some distance. That's field. Volts per meter. Okay, so what's that? This goes up, so it becomes U squared. Okay, keep this in mind. All right, good. So electron current density, then from before, we saw this, again, from my expression here, we saw this as well. It's Qn mu n Ex. So to compute the total current density, recall there are both electrons and holes. We need to do this for both carriers separately and add them up. Okay. So you have the electron current, which is basically N times mu n times Q times electric field, plus the hole current, P times Q times mu P times Ex. Okay, that's why we need to know about the electron concentration and the hole concentration. Okay. Also remember, in the very simple video we saw, electrons were moving opposite to the field, the holes were moving with the field. Which way is the current flow? Which way is the current flow? With the holes. Okay? Okay, this is very important. We will come back to this. In fact, we'll come back to this in a few minutes. But keep that picture, the video in mind, actually. Take a quick look at it while we are talking about it. Hopefully that won't mess up my presentation. Okay, let's speed up. Okay, look at that. Too bad you can't see very well, but the blue is moving that way. So the electrons, that's carrying negative charge that way. That's equivalent to having positive charge moving this way. Motion of positive charge is current. Okay, so the current is in the direction of the electric field. It always is in the direction of the electric field. What's more important here, oops, let me just point that out again, is that the direction of current for the holes is the same as the direction of current for the electrons. Not always the case. We will see lots of situations where that's not the case. But that's the case here, and that's why, let me go back here. This, you can do it this way. They just add up. We should be careful about the sign. Okay? We'll see some other situations later on. Now, what does mobility depend upon? The mobility depends upon Qt bar and Mn star. Mn star, of course, is the effective mass. It depends on the curvature of the band. So let's think about this a second, and we'll come back to the mean time in a minute. Mobility depends on curvature. So we look at the band curvature for gallium arsenide. You see it's a very strong curvature here compared to silicon, if you can think about that. That means the effective mass is low. Okay? The mobility is high. This, I just want to drive home again the point that this is actually an important concept because it's actually very relevant for even for research today. I picked a news article to relate this point. This is a paper that came out in January, 3 weeks ago, maybe, yeah, 2 or 3 weeks ago, okay? What they did, basically, was researchers demonstrated record-setting p-type transistor. Okay, just a group at MIT. I'm familiar with it. All they did was they made a transistor which had very, very fast response. Okay, very simple terms. All they did was they increased the mobility. The way they increased the mobility was they changed the band structure of the material. In this particular case, they actually stressed the material. This is germanium. The same principle. I just want to point out, mobility is a very important concept, and it's still, most advanced in research devices, people still think about this. So I want you to keep this in mind as we keep talking about these concepts. This is not just for a textbook. Okay. Again, this is from a couple of weeks ago. So very important. Okay, so the other term that's important is, of course, T-bar, which is the mean time between the collision events. So this, of course, depends on temperature and impurities, and we'll look at how the dependence is. But you can see if you have more impurities, you have more collisions, so T-bar goes down. T-bar goes down, mu goes down. Not so good. Okay, so purer the crystal, better the mobility. It's one way to think about it. Also, we have to understand how it varies with temperature. Okay? That's the last part of this. So, catch up to it. So, let's look at drift from and define resistance. Okay? We'll talk about how current flows in a slab of semiconductor. So, imagine a slab of silicon, let's say, as shown here. You apply a voltage, current flows. Okay? So let's think about the current. You apply electric field here, the positive terminal of the battery here, negative terminal of the battery here. After the electric field is pointing in that direction, right? Left to right. Everybody see that? Should be very familiar with this because this comes from your high school physics. Okay. So you have a total electron concentration in this material has to remain constant because the material is charge neutral. Right? You cannot have and it's also a steady state. Two things, okay? And it's charge neutral, so electron and hole concentration have to be constant over time. It cannot change. Okay, keep that in mind. Of course, we know that the electron motion will be opposite to the field. The hole motion will be with the field. So far, we know. Very straightforward. But let's see what happens inside the semiconductor we talked about so far. What happens at the contacts? What happens at the edges? Okay. Okay, sorry. Before we go to that, forgot. We have to define a few terms. Resistance. Resistance of this bar is given by the resistivity of silicon times the length of the material divided by the width of the material. Area of the material, so width times thickness. Okay. This is very straightforward. Okay, time? Okay, we have time. Okay, so this is just the definition of resistance. Okay, let me just step back again. Resistance is just given by the resistivity of the material times the length of the material divided by the area, which in this case is that, face. Okay, that's pretty straightforward. So R is rho L over WT. L over WT times 1 over sigma. Sigma is the conductivity of the material. It's related to the resistivity, just reciprocal. Okay. In that case, now let's think about, so that's electron motion, we said that. The electric field direction is the whole motion, we already said that. What happens to the contacts, like I said before? Okay. For simplicity, and we'll talk about this again and again, we assume the contacts are ohmic. Now, what does this mean? It just means that the contacts equally attract electrons and holes with no preference. So if electrons come, the contact will take it. Holes come, the contacts will take it. Equally. No preference. Okay? So it's a perfect source or a sink. Source meaning it can also give electrons perfectly for electrons or holes. Of course, that's an idealization. We'll talk about real contacts later on. This is the assumption right now. Okay. So what happens at the contacts? Let's look at the two sides. At this side, an electron essentially comes up here and leaves the bar and flows through the circuit. Goes to the battery, another electron comes. Okay. For each electron that leaves here, one electron comes in, so the total electron concentration is a constant. Okay. What happens to holes? A bit more complicated. Okay, electron enters here. Okay, let's talk about what happens to holes. Here, a hole comes, okay, follows the field, comes here, comes here. Of course, holes cannot travel into an external circuit because they don't exist. An external circuit is typically a metal, right? Holes cannot exist in a metal. Okay, because the bands are overlapped, do not have holes. Okay, so when a hole reaches this contact, the picture of reality is that an electron comes in from the contact and recombines with the hole. That's the same thing. A positive charge going this way is the same as a negative charge coming this way, from a current perspective. Okay? That's the physical reality that we will assume. Not exactly the case, because we'll talk about real contacts later, but that's the assumption. Okay? The electron comes from the external circuit. But of course, if an electron comes in, electron has to go out on the other side. But for the holes, not for the electron current, for the hole current. So what happens on the other side? On the other side, an electron-hole pair is generated at the contact. And the hole goes into the semiconductor, and the electron goes out to the semiconductor, into the circuit. So remember, so an electron came in here, electron left here. But here, the electron that came in recombined with the hole. Here, an electron-hole pair was generated, and the electron left. Again, the total concentration of holes is constant, just like for electrons. So that's the approximate physical reality that we are going to see. Okay. With that, I think I'm going to stop there. For a few minutes, but yeah, I think I'll stop there just because the next part, it's just the last part. We'll talk later. Okay. So a few announcements. Remember, the problem set's due on Monday, and you can either email it